a video about reaction mechanism, and in order to understand the importance of reaction mechanism, we have to look at our overall reaction. So if you think about all those reactions that you have balanced in previous chemistry class, those are your overall net reaction. That means that you have your reactants and how somehow those reactants will interact with each other, will produce your products. So in a reaction mechanism, it's similar to your net reaction, but then it's actually breaking down that entire overall reaction into different steps. And why we need to look at the different steps now is because the different steps actually will affect the rate of reaction, because some steps will be really fast, some steps will be really slow. And we're going to look at how those will determine the rate of reaction. So reaction mechanism, here's an example. This is looking at hydrogen peroxide, and this is the decomposition of it. And you can see that I have two elementary steps here. This is the first step and this is the second step. That means that in order for your hydrogen peroxide to decompose, it actually takes two different steps. So the first question usually is, what exactly is the net reaction? What is happening here? And in order to find out what the balanced net reaction is, we have to cancel out all the reactants that were introduced with the products that we use. Basically, we're going to find whatever's on the left side of the reaction, cancel out with the right side. And we can see that there's one iodine ion here, and that will cancel, and also ion and ion here as well. So we cancel all that. We're going to see that on the left side, we're going to collect all these ones. So we have 2 H2O2. This yields 2 water molecules plus 1 oxygen molecule. So this is my net reaction. So if I have 2 hydrogen peroxide molecules, it will decompose into 2 water molecules and 1 oxygen molecules. What else we can have in your reaction mechanism in your steps is that you have something called intermediate. So these are products that will be formed and will be used up in the reaction, and you won't even see it in the net reaction. So how you can identify this is that it's going to show up as a product, and then immediately after that step, it's going to become your reactant, because it's going to produce that product, and then your reaction is going to use that intermediate for the reaction. So can you identify any of these on the product side that will, show up in the reactant side? And you can see that, let me change colors here, that for the ion here, it shows up as your product, and then immediately in the next step, it shows up as the reactant. And what happens is that you don't even see this in your net reaction because it gets canceled out. So your intermediate in this one is your ion. Another one is your catalyst that you need to identify, because catalyst will actually get introduced to your reaction. Like, you put your catalyst in, and then it speeds up the reaction, and then it won't get used up in your reaction. So in a catalyst, how you want to identify is that it's going to introduce the reaction on the reactant side, but it's going to use up in the reaction, as in that it will help the reaction go faster. It won't, I guess I shouldn't say that it will be used up, as in like it won't be like 100% used up. It will still show up as your product. So in this reaction mechanism, you're going to see that for your iodine ion, you introduce this, it helps the reaction to speed up, and then it shows up as your product. So I guess I shouldn't have said that it's used up in the reaction just for technical terms. It's just more like the reaction uses it. So your iodine ion is your catalyst in this sense. And how it does that is it lowers the activation energy. So if you remember your potential energy curve, this is the sample endothermic curve. And if we were to draw a catalyzed reaction, it's going to start off the same because it's going to introduce the catalyst. How it speeds up the reaction is that it lowers the activation energy. So this activation energy is actually lower than the initial one. So that is how catalysts work, and that's how you identify it. So the next example here is here's another one, has 3 steps. So this is first step, second step, and the third step. And then this one actually indicates the rate of each of these elementary steps. This one is a slow one, this one's a moderate one, and this one is a fast one. Well, what do they mean? Well, let's look at the net reaction first. Let's just cancel out all the ones on the left side and the right side and see what our net reaction is. I can see that this I1 is in the product and this is in the reactant, so we can actually say that that's an intermediate. And here's another intermediate. I2 shows up in the product and shows up in the reactant in the next step. Anything else? I don't think so. I think it's just 2P plus Q plus S. This yields T plus R plus W. And I don't think we have any catalyst because there's nothing that's on the left side will show up in the product step. So then here's the key thing here is that what's the rate determining step? The rate determining step is the step actually that the rate will basically be determined by. And when we have these three elementary steps, it's always the slowest one. This one is your RDS. One example that I think about rate determining step is that if you're a hockey fan, if you know one of those players that likes to put on their equipment really fast, you put on your skates and then all your equipment, you're ready to go, and then you get onto the ice and then you realize that you can't get onto the ice because the Zamboni person is still icing the ice, right? It's still Zamboniing the ice. So that person who's Zamboniing the ice, taking the Zamboni around the ice rink, that's the rate determining step, because it doesn't matter how fast your team dresses, put all the equipment on, you can put up really fast. It depends on the person driving the Zamboni, because the Zamboni driver is the one that allows you to get on the ice. So that Zamboni driver is the rate determining step. And it doesn't necessarily have to be the first one that your rate determining step, could be your second step or your last step. It's just a matter of how the nature of the reaction. So here's a couple situations. This one says that increasing the concentration of P is right here, will increase the rate of net reaction. Is this true or not? We can say that this one is true because if we increase the concentration of P, we're increasing the concentration in the rate determining step. That means we're making the Zamboni guy drive faster. And if the guy drives faster, then all these rate will be increased. And it doesn't matter if the P is here, as long as your concentration is increased in the rate determining step, your overall rate will increase, because like I said, the Zamboni guy is driving a lot faster, so your team can get on the ice a lot faster. The next one is increasing the concentration in Q. Again, Q here is in the rate determining step. Same thing, so you're basically increasing the Zamboni guy's driving speed. So this will also increase the overall rate reaction. And the third scenario is increasing S, whereas S is in the fast reaction. That means that that's you putting your equipment on really fast. So you can put on even faster, but still it doesn't matter, because you can put on really, really fast, you get on the ice, the Zamboni guy is still icing the ice, and it doesn't matter, you still can't get on the ice, so the rate of reaction is still really slow. So this has no effect. So this is true because it has no effect because you're not at the rate determining step. Q is true because it's at the rate determining step. So that's how you read and interpret rate or reaction mechanism. So hopefully that has helped you. So see you again.